Welcome back to Business Mathematics 2, MA 1203. So for today, we are still going to discuss about first order difference equation. Specifically, we are going to talk about the stability of our solution. So generally, the function yt changes over time, but there is a function yt that doesn't change with time. The solution is called the steady-state solution. So the steady-state solution is defined as a function yt that doesn't change with time. It means yt plus 1 equals yt, and this applies for all t. So you have y0 equals y1 equals y2 equals y3 and so on. And for the general first order linear autonomous difference equation, this one, with a is not 1, so you have the steady state solution is given by this. How do you know this? Let's see. So you have yt plus 1 equals a yt plus b with a doesn't equal to 1. So maybe the first one, the simple one. If a is 1, so you have yt equals y0 plus b times t, isn't it? So can you have a steady state solution, the solution that's still the same, that doesn't change with time? Can you have? Don't forget t is time. So if you have t1, it will change this. Okay, yeah? It will not change if b is 0. So if you have when a is 0, you can have steady state solution. What is the steady state solution? This is the steady state solution. Yt equals y0 if b is 0. Okay, yeah? Very easy. What about when a doesn't equal to 1? When a doesn't equal to 1, don't forget yt plus 1 equals yt for all t. This means yt plus 1 equals yt equals a yt plus b. So this is 1 yt minus a yt equals b. You can factor out yt, so you have 1 minus a equals b. So you have yt equals b divided by 1 minus a. So this is what we usually call the steady state solution. The steady state solution. Okay, so this is the for all a doesn't equal to 1. So this is the steady state solution. When a is 1 and b is 0, the steady state solution is yt equals y0. Okay, so you have already know what is the steady state solution and how to find one using the formula. But what does it mean? What does the steady state solution mean? Okay, let's see the solution, the explicit solution of this one. The general first order linear autonomous difference equation. Okay, and the solution is given by y0 plus bt if you have a is 1 and if you have a is not 1, you have a to the power of t y0 plus b times a1 minus a to the power of t divided by 1 minus a to the power 1 minus a. Okay, so okay, so we are going to talk about when a is not 1. When a is not 1. So you have yt is a to the power of t times y0. You can multiply this 1 by 1. Yeah, you choose this and multiply this 1 by 1. So the first term is b divided by 1 minus a times 1. So you have this b times 1 is b. Okay, yeah? B over 1 minus a times minus a to the power of t. So you have minus b a to the power of t of 1 minus a. So There you go. This is your steady state solution. Okay, the question is, in the long run, when t goes to infinity, can my solution go to the y steady state solution? Can my solution go to the steady state solution? Can I have? We usually say, can yt converge to yss? Can yt go to yss as t goes to infinity? And the answer is yes. Don't forget, if you have a to the power of t, it will become go to 0 as t goes to infinity if a is between -1 and 1. So it will go to 0, and it will leave out y steady state solution. So when a is between -1 and 1, yt in the long run will converge to the steady state solution. But if a is greater than 1, a is less than -1, a is 1, a is -1, you cannot have your yt goes to minus infinity. So it will give you diverge. It will not go to the steady state solution. This also, but this is special case. When b is 0, yeah, it still can go to your steady state solution because your steady state solution is your yt. That's obvious, isn't it? Okay, so you have this as your, okay, the solution can converge or diverge. Diverge can be plus or minus infinity, or converge to not a certain value. So when a between minus and 1, 1 and 1, so your solution will go to the steady state solution, will converge to the steady state solution given by b divided by 1 minus a. But when a is 1, yeah, it will converge when b is 0. When a is less than -1, greater than 1, or equals -1, you will have your solution will diverge to plus infinity, minus infinity, or converge to not a certain value. Okay. Last one. I think this is the last one. Okay, the last one before we will talk about the example on the price adjustment model. That is, how does it converge? Will it converge monotonically or oscillatory? Okay, let's look at this. Okay, don't forget our solution have something like this. A to the power of t times something plus something, this is just a constant, plus a constant, something to the power of t, yeah, something to the power of t, yeah, b. Okay, let's see if we set b equals 0 first. B equals 0. So I just look at a constant times a to the power of t. Constant times a to the power of t. Let's see. So if you have yt equals maybe the first case when a is greater than 0, let's see that a is a half to the power of t. What is this? You have this one, yeah, 1 a half. When 2 you have 1 over 4, 3 1 over 8, and then you go to your steady state solution, that is y t equals 0. Okay, because b is set 0. So your steady state solution is 0 divided 1 minus a. Okay, what about when yt equals to the power of t? Okay, you have this one. This is t, 1. When 1, 2, and 2 to the power of 2 is 4. 2 to the power of 3 is 8. So it will go in this trend. It will monotonically up or monotonically down. Monotonically increasing or monotonically decreasing. So if you have A is greater than 0, you have a monotone sequence. You have a monotone sequence. Your number should be increasing or decreasing. What about if I have this case less than 0? Let's see. This is T. This is YT YT, okay. A, so I choose minus a half to the power of T. What is this? When 0, you have 1. Okay, you have minus a half. This is. When 1, you have minus a half. When 2, you have 1 over 4. When 3, minus 1 over 8. 4, okay, so you have this trend. Up, down, up, down, but it will converge to 0, the height of 0, yt equals 0, because b equals 0, yeah? So the steady state solution is 0. Okay, so if you have a less than 0, if you have minus half, then it will converge oscillatory. Oscillatory. What about when a is minus 2 to the power of t? You have this one, and you have minus 2 here, and then plus 4, minus 8, plus 16, and so on. And so you have an oscillatory, but it won't converge to a steady state solution. Okay, so if your A is greater than 0, if your A is greater than 0, then you have a monotonous sequence. You have it will increase or decrease monotonically. It will converge or diverge monotonically. But if you have A is less than 0, you can have converge oscillatory or diverge oscillatory. Okay, yeah? Okay, let's look at this price adjustment model. This is the example. Let the number of commodity demanded for the society at time t is, so this is the quantity demanded at time t, demanded, equals the constant plus b times the price at time t, when a and b is positive constant. Positive and negative. Okay, b should be negative. Why? Because this is a demand. Demand function should be a decreasing one. Decreasing is from b, so b should be negative. What about the number of commodity supplied, quantity supplied at time t by the producer depends on the price of the previous time. Okay, E t minus 1 of pt, the expected price from the previous time t minus 1. Okay, yeah? And G and F should be positive. Why? Because you expect this, the supply function should be an increasing function. So F and G should be a plus, a positive constant, non-negative, yeah? And how you supply a market, it depends on what your expectation on your previous period of your price. So this is what you mean by ET minus 1 PT. So it depends on the expected price at the previous time, T minus 1. It makes sense, isn't it? Doesn't it? Okay, so if you want to have, okay, the simplified model, ET minus 1 PT is PT minus 1. So if you want to talk about the price equilibrium, the quantity supplied at time t should be the quantity demanded at time t. So you have this one, okay, yeah, and you have this one, and you have this one. So you have, this is difference equation, first order. Don't forget, this is just a constant. This is just constant. So you have A pt minus 1 plus B. You can shift the time. So you have pt plus 1 equals this plus pt. You can shift the time by 1. So you have plus 1 here for the time and plus 1 here. So you have pt plus 1 equals this plus this times pt. Okay, yeah. So this is just a first order difference equation. With A is G over B. Don't forget B is negative. And with A is F minus A divided by B. Okay, yeah. And how do you find the solution? You can find the solution. Try to find the solution, this. Okay, try to find the solution. And try to find the steady state solution. If you have already find the steady state solution, you have to check whether this is converge to the steady state solution or it will diverge. If this is converge or diverge, you have also to know whether it converge monotonically or oscillatory or diverge monotonically or oscillatory. Okay, yeah. So this one, the general form that is on the non-autonomous, but we won't discuss about this. Okay, you can look at this at your textbook, but we won't discuss about this. Okay, that's all for this chapter that is on the first order linear autonomous difference equation. In the next session, we will talk about the second order linear autonomous difference equation. Thank you very much.